Pronto, estamos a ouvir, professor. Pode iniciar.
So, good morning, everyone. Welcome to session 4 of SBESC 2021. So it's a pleasure to be with you today. This session 4 is about distributed system and fault tolerance. I am Professor Alisson Brito from Federal University of Paraíba. I'm the chair of the session today. I'm professor in the computer engineering and he also member of the graduate program of computer science and mechanical engineering here at UFPB. So it's a pleasure to be with you. So we have here 6 excellent papers to present. So we are glad to have all the authors here. So I hope you have a very good morning and enjoy all the papers. Each paper will be presented by one of the authors, and after the presentation, we are open to questions. So be free to write on the chat, or maybe ask for talk here in the session for those who are present. So let's then begin with the first paper. The first paper will be presented by Gabriel Nazar. The paper is named Lightweight Dual Modular Redundancy through Approximate Computing. The authors are Gabriel Nazar, Pedro Cooper, Marcus Leibniz, and Ben Uhling. So, Gabriel, welcome to our session, and we are present your video here. So let's begin.
Hello, my name is Gabriel Nazar, and in this video I'll be presenting our paper entitled Lightweight Dual Modular Redundancy through Approximate Computing. Approximate computing is a broad set of techniques that can be applied at different abstraction levels to exploit application error resilience, which is the property of some applications that can still use computational results even though they are not completely exact. So basically, these approximate computing techniques will exploit precision reduction to improve performance or to reduce costs. And approximate computing can also be used to reduce the costs of redundancy in fault-tolerant systems. So for example, if you have a triple modular redundancy system, you can use one exact design and 2 carefully designed approximate copies that through a voter will try to always produce the exact output in fault-free scenarios. And since these copies are approximate and less costly, the overall system costs are also reduced. But these approaches, they still aim to provide the exact output even in fault-free scenarios, and therefore they are not fully embracing and exploiting the benefits of approximate computing. Conversely, in this work, we fully embrace approximate computing, aiming at further minimizing implementation costs. By focusing on error-tolerant application domains, our goal is to minimize the output error induced by faults by accepting that degraded outputs may be produced even in fault-free scenarios. So costs are minimized by relying on dual modular redundancy, or DMR, instead of TMR. So basically, we are eliminating the need for an exact design in our system. We're using 2 approximate copies. Actually 2 identical approximate copies in this case, so that we are able to maintain the full coverage of traditional DMR approaches. And we are using only approximate designs which have themselves reduced costs. Regarding how voting can be done in such a system, 2 voting schemes were devised for systems with different performance constraints, as will be seen in the remainder of this presentation. So this is a brief outline of this presentation. We'll see an overview of the system architecture that we have considered and the 2 voting and checking strategies that were devised for this system. And then we'll see how these techniques were integrated into a high-level synthesis tool chain. Then we'll see experimental setup and experimental results. And finally, we'll discuss the conclusions and future work. The architecture we have considered in this work is a homogeneous parallel accelerator composed of multiple processing units. And these processing units are generated with high-level synthesis. And as is usual for HLS-generated designs, they include not only data outputs, but also a done signal that indicates that the internal finite state machine of each processing unit has reached a conclusion state. So this done signal will also be used by the checking modules, as we'll see in the following slides. Besides that, the architecture also includes a global control logic that triggers the acquisition of new inputs and new outputs by a conclusion state. So this done signal will also be used by the checking modules, as we'll see in the following slides. Besides that, the architecture also includes a global control logic that triggers the acquisition of new inputs and new outputs by the input and output buffers. And it does that periodically, considering the worst case execution time of processing units, which is determined by means of worst case execution time analysis. It should also be noted that these processing units typically have narrow outputs. So for instance, if we have an image processing unit, it will typically produce one or a few pixels at each cycle. So it's not a very broad output. It is an output that is produced iteratively through many cycles for each new input being processed. And this will also be used by the checking modules to accumulate the effects of faults depending on the adopted voting strategy. The first voting strategy we will discuss is direct average voting, and it consists in computing the average of the output of both modules. If both modules produce the same output in a regular scenario with no faults, then their average will also be the same, and it will be used as the output of the checking module. If one of the modules, however, was subject to a fault and produced an incorrect output, then under the single fault hypothesis, we can assume that the other output is correct, and therefore their average will reduce the impact of that fault. So that is the goal of direct average voting. Moreover, the done signals produced by the modules are used. If by the time the worst case execution time is reached, one of the modules failed to raise its done signal, we can also assume it was subject to a fault, and we will disregard the output of that faulty module using only the output of the other one. And this will be done by these two multiplexers. So as a result, direct average voting always produces an output within the worst case execution time predicted for that application, being recommended for those scenarios in which a delayed output is unacceptable, and an output must be produced within the expected worst case execution time. Conditional average voting and recomputation is the other voting strategy, and it is slightly more sophisticated. It will try to mitigate those faults that output is unacceptable and an output must be produced within the expected worst case execution time. Conditional average voting and recomputation is the other voting strategy, and it is slightly more sophisticated. It will try to mitigate those faults that cause particularly highly erroneous outputs. So for each output that the processing units produce, the absolute difference will be computed and accumulated. And if this value exceeds a threshold that is defined by designers, then we will trigger the indication of a critical error, and a recomputation will be triggered to eliminate the effect of faults and produce correct outputs, assuming that the faults were transient. So this circuit operates in addition to the traditional direct average voting circuit. So we are also using the average of outputs even when observing the effects of faults that do not exceed the threshold. As a consequence, since this approach uses recomputation, it may exceed the predicted worst-case execution time. So it is recommended to those systems in which delayed outputs can be occasionally accepted and they are less critical than a highly erroneous output. Okay, so we have voting techniques for approximate designs, and now we can discuss how we can produce approximate designs using high-level synthesis. So this is a standard high-level synthesis tool flow. Basically, this is the leg up HLS tool, which uses the LLVM compiler front end, and then its own backend to produce Verilog synthesizable RTL code. And these intermediate representations are optimized through standard compiler optimizations and are the main input to our own approximation technique. Basically, what the approximation technique will do is that it will apply variable to constant substitution. It is the approximation technique that we have used here. It basically replaces operations with constant values, and we're going to do that for each instruction individually, and also apply standard compiler optimizations that may be enabled by this approximation. And with that, we will have candidate intermediate representations, and with these candidates, we can estimate area, performance, and error. Of course, that performance estimation is very complex because we are employing worst case execution time. So we need to run the backend and then implicit path enumeration technique, which is the worst case execution time analysis we have used. With that, we have our worst case execution time that is used to compute our fitness function. And then we're going to choose the candidate instruction with highest fitness, considering area, performance, and error as the chosen approximation. And with that, we have one approximate intermediate representation that can go through the backend tools to obtain a final design. And we can repeat that, approximating additional instructions, producing designs that are further approximated, but also that have lower cost and higher performance. And since the approximation technique provides gains both in area and performance, we can use them together to improve the overall architecture throughput. When we reduce the area, we make available some saved area that can be used to instantiate additional processing units within the same overall area. And since these processing units are individually faster, the global control logic can trigger input and output buffers at a higher frequency. Regarding experimental setup, we have used Cyclone 5 FPGA devices with Quartus 5 for the FPGA synthesis. We have used 6 benchmark applications from CHStone and XBench benchmark suites, from image, voice, and video processing domains. And we have used input vectors from the ITU and the USC databases. And we have performed fault injection with IR instrumentation. So we instrument the intermediate representation code to inject faults in the outputs of each operation. Moving on to experimental results, here we have the individual results for each benchmark application, considering area, worst case execution time, overall architectural throughput, and mean squared error. So as expected, as we iterate with our approximation heuristics, we introduce more error and we improve the throughput by reducing the worst case execution time and by reducing the area of each processing unit. So for instance, if we consider a target mean squared error of 500, we can see that on average, the throughput is improved by 55% compared to that of exact DMR approaches. So by employing approximations, we have a 55% better throughput when compared to a DMR composed of exact designs. and also analyze the effects of faults on output errors and the ability of average voting, and in this case direct average voting, to mitigate these effects. We have here exact designs and also approximate designs after a certain number of approximations. So we're looking at 1, 5, and 10 approximation iterations. And we can see here that, well, as expected, as we have more approximations, we have higher error, and we have also the impacts of faults that compound, that stack with the effects of deliberate approximations. But the interesting part here is that, as expected, direct average voting is able to revert the effects of faults, bringing the output error much closer to that of fault-free operation. The effect of faults on output can be seen by means of the increase in the mean squared error. And this increase is very substantial, especially for designs with less approximation, but it is also substantially reduced by the use of direct average voting. And now to evaluate the impact of recomputations on the output error, we can see the results for conditional average voting and recomputation for different recomputation ratios. So as we increase the computation ratio by reducing the recomputation error threshold, we have, as expected, a reduced mean squared error. And the most interesting and desirable property is that most gains are obtained with a low recomputation ratio. So most of the error is able to be mitigated with a low recomputation ratio. And this is a summary of results. So we have the average mean squared error degradation due to faults for different approximation levels, for unhardened designs, for designs with direct average voting, and for designs with conditional average voting and recomputation that use a threshold that cause 25% of the errors to trigger recomputation. And we can see that we have a very decisive and progressive reduction in error degradation induced by faults. So we have concluded that by using only approximate designs and avoiding stratification, low-cost redundancy can be achieved. And even though faults may severely increase the output error, this effect can be substantially reduced with or without using recomputations. Future work includes using other approximation techniques and other voting schemes found in the literature, especially those that target specific applications. For example, machine learning applications are, of course, a very interesting domain to be evaluated in future works. With that, I conclude my talk. I thank you for your attention, and I will be glad to take any questions.
So, thank you, Gabriel, for your presentation, your video. So we have some minutes for questions. So we are open. So
hi, Alison.
Hi, Gabriel. So meanwhile we can wait for some other questions, but I have some questions for you. First of all, congratulations for your work. It's very interesting. One general doubt is from your experiments, I understood that your approach is more suitable for, or at least used mostly for multimedia application where there are more fault tolerance in the session of the data. So do you consider this application is limited to this kind of scenarios, or do you see that it might be possible with some improvements to extend to other scenarios?
Since this work is more closely related to approximate computing compared to previous work that used approximate redundancy. Our work it will produce faulty outputs, approximate outputs even when no faults have affected the system, because we are relying solely on approximate instances of our design. So in its current form, it wouldn't be advisable to use this technique for application domains or specific applications in which an absolutely bit level precise output is required. So this approach will find most of its benefits in these domains in which some level of imprecision can be accepted. And the whole idea of the work is to try to reduce the average degradation that can be introduced by faults, considering that, well, in the event that we do have a fault, we don't want it to severely degrading the output, right? Even if we have a fault, it may still be the case that our output is still usable, and our goal here is to try to maximize the chances of that happening.
Yeah, great. I don't think we have all the questions from the audience. Maybe I can make it a very short one. So you also mentioned in the end that you see that maybe it would be possible to use some machine learning approaches. It's how do you see that? How could that be used? And if you figure out about the cost, I mean, computing cost of adding this kind of.
Basically, there are some other works that have realized that machine learning. Machine learning is one of those domains in which, well, some level of error can be accepted, even though we haven't looked into machine learning applications in this particular work. Let's say we have some object recognition based on image, based and it's implemented with some sort of deep learning, convolutional neural network, and so on. And given that if we have a fault, but this fault does not cause our classification to go wrong, let's say the correct fault-free neural network would be able to correctly classify that particular image. If we have a fault, and even with this fault, the classification is still correct, this is not as critical as if the fault causes a misclassification. So basically, well, given that many have also looked into implementing neural networks and machine learning applications in general in FPGAs and also using high-level synthesis, it seems kind of natural that this approach could be evaluated for that particular application domain, trying to, with minimum user intervention, as is typical for high-level synthesis-based approaches, to try to produce a circuit that has a reduced probability of giving a misclassification, an incorrect classification in the event of a fault.
Great. Thank you, Gabriel. We are.
Thank you, Alison, for your introduction and your questions.
Yeah, you're welcome. We are open for questions for Gabriel in the chat or in the YouTube chat, or you can contact him directly if you have further questions. We have a time pressure to follow to the second paper. So thank you again, Gabriel. So
thank you, Alison.
Welcome. Let's jump to the next paper. It's named BASE, a blockchain-based access control at the edge for industrial control devices of Industry 4.0. The authors are Charles Carrocho, Karine Oliveira, David Sena, Carlos Frederico Cavalcanti, and Ricardo Oliveira. So let's play the second work.
Hi, my name is Charles Tim Batista Garrocho, and I am here to present my work. This work was created at the iMobile laboratory, which is located at the Federal University of Ouro Preto in Brazil. And it is also a joint work with the Technological Institute of Vale. This work is titled BAS, Blockchain-Based Access Control at the Edge for Industrial Control Device of Industry. The Industrial Internet of Things is expected to attract significant investments for an industry. In this new environment, the blockchain has immediate potential in industrial applications, providing unshakable, traceable, and auditable access control. However, recent work and present in blockchain literature are based on a cloud infrastructure that requires significant investments. Furthermore, due to the placement and distance of the cloud infrastructure to industrial control device, such approach present a communication latency that can compromise the strict deadlines for accessing and communicating with this device. In this context, this paper presents a blockchain-based access control architecture, which is deployed directly to add device positioned close to devices that need access control. The blockchain network is a decentralized peer-to-peer network, which no points of failure where transactions cannot be deleted or altered. Blockchain is highly scalable and all transactions are encrypted, making them secure and auditable. At the heart of this technology, there are consensus algorithms, which are protocols for achieving reliability in a network of several untrusted nodes. Smart contracts are computer protocols designed to facilitate, verify, or enforce digitally the negotiation or execution of a contract. Ethereum, Hyperledger Fabric, Hyperledger Salto, and Corda are popular smart contract platforms that are contributing significantly to the generation of dApps. As shown in the figure, dApps carry the blockchain network through a node that executes the smart contracts for the ledger access. The fourth industrial revolution is based on internet connections, allowing the integration and incorporation of manufacturing machines. This scenario represents a challenge, as industrial processes depend on the elements that are triggered in real time and synchronized. In this context, data allocation and processing becomes a significant challenge as centralized communication architecture have high network traffic and high latency due to the large volume of industrial data. To maintain stability and control performance, these industrial applications impose stringent requirements on data communication between many network nodes. In this context, edge computing can reduce network latency use by reducing the communication distance between devices. Most blockchain and smart contract technologies today have throughput and latency constraints on their operation, which require some time to react to consensus for transactions to be carried out effectively. The works in the literature do not take into account the stringent requirements imposed by industrial systems, such as real-time systems. Given this research gap, we propose the BAS architecture that aims to reduce the communication delays between the blockchain network and access to time-sensitive industrial devices. Furthermore, unlike the works in the literature, BAS was performed and evaluated in a real industrial mining environment. BAS architecture is designed to provide access management for industrial devices, In this sense, the BESC architecture is represented by 5 main components: user, device to access the resource. This device can request the execution of operation or reading of data from a resource. Resource, industrial device that controls and monitors industrial machine and process. Requests for access to this device are forwarded to the blockchain network for identity validation of access to resource. Blockchain edge node, device that contains functionality necessary to establish a blockchain network. Auditor, workstation that can monitor and track all transactions and their respective identifications. Further blockchain edge nodes. Different blockchains edge nodes can be distributed in the industrial plant and connected by an Ethernet network. This figure illustrates the working sequence for accessing an industrial device through the blockchain network. The user requests access to the industrial device. The industrial device dep sends the user request to the blockchain node. Through a smart contract, the blockchain node validates and records the user access to the ledger. The industrial device dep receives the response and allows access to the user. User access to the industrial device differs from auditor access to transactions. To access transactions, the auditor sends a request to the blockchain node. The blockchain node carries the transactions in the ledger without executing the smart contract. The auditor receives transactions from the blockchain node. To evaluate the BESC experiment were carried out using a proof of concept in an industrial mine environment. This figure illustrates this environment that consists of iron ore plant in which the wagons are weighed in motion by scale. Generally, the controller device of a scale are closed boxes, and the cost of maintenance is expensive. Therefore, the development of an open-source controller device for the scale will bring flexibility and cost reduction. However, the ease of making changes to the control logic becomes a point of attention with regard to the integrity of the data measured by the scale. In this context, the measurement result may not be reliable due to the changes made. In view of this problem, it is proposed to apply the blockchain to reduce any change in the control logic or change calibration coefficients in the scale, making the system transparent and auditable. Our implementation features a test environment that can be assembled using the Docker Compose tool. We build a container for each actor in the scenario shown figure. We defined on auditor 2 users, 2 scales, and 3 blockchain nodes of the Hyperledger Salto platform. Blockchain platforms are built for server and not IoT device. Thus, it was necessary to carry out a recompilation process of the entire Hyperledger Salto platform for embedded device. The table shows the hardware and software specification of the device used in the experiment. Delays in sending transactions from each controlling device to the blockchain network were measured. Titled executions were performed in each scenario. Each scenario, blockchain nodes are deployed on embedded device and positioned at a distance of meters from the controller device. Cloud scenario. Blockchain nodes are deployed on a cloud server and positioned at a distance of miles from the controller device. The following metrics were measured: create, total delay of control device for transaction preparation. Send, total delay for transferring the transaction from the controller device to the blockchain network. Latency, total delay from receiving the transaction to confirmation that the transaction has been committed by all blockchain nodes. Carry, total delay in carrying a transaction for the blockchain networks to the controller device. It is important to note that the total delay for the blockchain network to give a response regarding the request for accessing to a controller device resource is represented by the sum of the delays of the create, submit, latency, and carry operations. While the total delays for the auditor to read the transaction in the blockchain network is online represented by the delay of the carry operation, since it is not necessary to create a transaction nor executing a smart contract. The figure shows the results of submit, latency, and carry operations delay found in the scaled blockchain system. The results show that the integration of blockchain edge computing in an industrial environment can result in better performance than a cloud-based approach. The edge scenario that represents base presented sufficient runtime for several industrial applications that not have tight deadlines. However, for applications that need shorter lead times, the high standard deviation, particularly from latency operation, can make base insecure. In addition to the total time of each scenario, this figure shows the time and standard deviation of each operation, which represents the variability of the data found in the experiment. Considering the behavior of the latency operation in the edge scenario, it is possible to observe an increase in the time of this operation in this scenario. As can be seen in the results presented, the variability of the data makes the system unstable, especially in latency operation. Thus, every time a request for access to a control device is made, it will result in the unpredictability of its realization in industrial applications that have real-time deadlines. This time variation can affect the time required to access a controller device resource, which can delay decision-making and compromise system time constraints. Blockchain has the ability to revolutionize the industry. However, current blockchain architecture is designed for a cloud infrastructure, present communication delay users to meet tight industrial process deadlines. In this context, a blockchain-based access control approach has presented, in which blockchain nodes are deployed on edge device. Through performance evaluations in a real mine environment, the edge-based approach achieves a shorter runtime for accessing an industrial device compared to the cloud approach. Despite the better performance, there is a need to find alternatives to them that can reduce the standard deviation of time to access an industrial device. One possible way to reduce access time variability is to incorporate new distributed ledger technologies such as Tangle and Hashgraph. Here I end this presentation of my paper. I am here to ask questions. Get in touch via my email. Thank you very much.
So, as there is no author from the paper present, I guess. So, if you have some question, you can write directly to the author. So then let's go to the next paper. We have short changing in our program due to requests from the authors of the third paper. So we are now switching to the fourth paper. The paper is Orca RT-Bench, a reference architecture for real-time simulators. The authors are Anderson Domingues, João Beno, Alexandre de Moraes Amorim, and Fernando Moraes. So the presenter will be Anderson Domingues. So please, let's play the video.
So hi everyone, my name is Anderson Domingues and today I'm going to show you some of our work entitled Orca RT-Bench, a reference architecture for real-time shadowing simulators. So here's the outline for this presentation. First, I will show you some introduction and motivation followed by the problems we found in the current scheduling simulators. Next, I present you our reference architecture. We will discuss each of its building blocks. Next, I will present you our implementation of this architecture and the models behind each of the building blocks. Then, I will close this presentation with some of the directions that we will take to improve our work. Real-time systems is an ever-increasing branch of computer science, and as such, it has delivered to the community a massive set of tools, techniques, and models. Deterministic behavior and predictability are core to the operation of real-time systems, both achievable through scheduling. The literature presents a vast number of shadowing simulators, which focus on basically teaching tools that support undergraduate and graduate students, and research and industrial tools, which focus on accelerating the development of real-time systems by practitioners and engineers. We researched the literature for tools and frameworks for the design of shadowing simulators. Although we found main tools, these tools lack of some properties which we understand to be necessary for the simulation of real RT systems. First, there are many old tools out there, built upon old technologies not supported anymore. Second, the available tools are poorly documented, which makes it hard to extend or improve this tool, preventing the implementation of new shadowing algorithms, for example. Third, most of the tools are ill-designed, lacking enough patterning of any strategy to control software versioning or growth, which also affects extensibility. Fourth, we found no standard for data exchange formats, so basically every single simulator has its own file format. Some of them rely on non-structured plain text formats. 50, we could not find a tool to support the modeling or emulation of interruptions and system calls, which we believe to be necessary for the analysis of real-time systems. The goal of this work is to support academics and practitioners in the development, analysis, and validation of shadowing algorithms by providing a reference architecture for shadowing simulators. First, we want to accelerate the analysis of existing real-time systems by providing features to simulate interruptions and system calls. Second, we provide a core implementation of a simulation to aid graduate and undergraduate students in their projects. Third, we present a method for performance assessment of discrete event-based simulators, which could be used as part of other shadowers, such as online shadowers. Our reference software architecture can be extended to derive new simulators from a base implementation. We opt for a component-based design, which enables the reuse of building blocks. Our architecture has 5 building blocks: event model, system model, simulation model, shadowing algorithm, and performance model, with the last one optional. The first building block of our architecture corresponds to the event model. The event model is the way the scheduler and running applications are presented within the system. Basically, we are interested in simulating 2 kinds of events. First, we implement the periodic shadowing interruption. This interruption is the base of most simulators, although they do not explicitly refer to this interruption in the software. The periodic shadowing interruption occurs on super time slice, where the time slice is the amount of time dedicated to the shadowing task, 1 per processor core. The second event that we simulate corresponds to the system calls. Basically, tasks can put themselves to sleep or simply end during the execution. In this case, the shadower must be invoked to select another task to run. We could not find a similar mechanism in any of the studied shadowers. The second building block of our architecture is the simulation model. The simulation model is the method used by the simulator to generate the simulation trace. A simulation trace is the result of a simulation session, usually including the name of events and annotations indicating the time they would occur. For uniprocessor systems, no two events can occur at the same time, so there must be an order of precedence between events, and failing in resolving conflicts between events may result in non-determinism. The third building block of our architecture corresponds to the system model. In the system model, a transition system dictates the state of the tasks within the system. At least two lists are necessary, as we must distinguish between running and idle tasks. We can describe the relation of lists as directed graph, a G-graph, whose nodes correspond to lists and edges corresponds to actions that move tasks from one list to another. Then, an scheduling algorithm is pretty the same as a sorting algorithm, which must put the next task to execute at the top of the list of tasks. The last building block of our architecture corresponds to the performance model. The performance model is optional, and it's not necessary for the simulation. The goal of the performance model is to enable the assessment of the performance of the simulator. Basically, we can compare two different simulators by comparing both simulators' performance models, without the needing of executing the same simulation in both tools. Some parameters of real systems can be included in the performance model. For instance, we know that the overall performance of the systems is connected to the parameters such as length of the task set and the period of rescheduling interruption. Changing either parameters also changes the number of calls to the scheduler during the hyperperiod. So we designed and implemented the tool to validate our reference architecture. The goal of this tool is to serve as a basic implementation of our models, as well as a standalone simulation tool. In this tool, we focus on the simulation of unit-processed systems only. The tool is written in C++ and have no dependencies on external libraries or frameworks, which makes this tool easy to install in any computer. The building blocks we have discussed so far reside in the tool's backend, which is also responsible for manipulating application and tracing files, as we see next. The backend part of the tool can be invoked from the command line, although we also developed a graphical interface for our tool, which we shall see later. So this is our implementation of a task model. A task is a three-tuple PCD where P is the task's period, C is the task capacity, and D is the task deadline. Such a model appears in many of the viable tools and also in academic books. Below we see the application description file, in which an application is represented. In our opinion, this kind of file format is easy to read and can be easily manipulated by both students and practitioners. The format can be modified and extended, and parsers for other formats can be included in the tool as well. This is our implementation of a system model. In this model, a system is represented by four lists of tasks. A transition system dictates the movement of tasks in the system, always from one list to another. For uniprocessed systems, only a single task can reside in the running list, which stores the executing tasks. The blocked list stores tasks that cannot execute due to I/O blocking. Finally, the read list stores all tasks that can execute, and is up to the scheduling algorithm to decide which one will move to the running list at the beginning of the next time slice. And this is our simulation model. Events, which can be either interruptions or system calls, are represented by a three-tuple TFT, where T is the release time of that event, F is an activation function, and T is the period increment. A priority queue of events keeps events sorted, where the next event to execute is always on the top of the queue. Once an event is popped from the top of the queue, the corresponding activation function adjusts the state of the simulation to reflect these changes generated by the execution of that event. Then the event is pushed back into the queue with the next release time incremented, so it can be executed later. This behavior repeats until the end of the simulation, which can be triggered by the user or through a system call event. Our simulation model is a 5-tuple T0, N, P, E, and G, where T0 is the current simulation time, which usually starts in 0. The time to simulate N, the priority queue of events P, and the set of all events E, and finally a computation function G, which advances the simulation to its next step. This is the performance model that describes the behavior of our simulator. By providing this model, we can predict the performance of the simulator and evaluate its scalability. This performance model has basically two components. The first one, at the left side of the multiplication, is the effort of calling the scheduler once. At the right side of the multiplication, we have the amount of times that the scheduler will be invoked during the hyper period. The scheduler is invoked once per time slice due to behavior of the periodic scheduler interruption. This is summed to the number of times that the tasks end, represented by the system calls once per task. As I told before, scheduling algorithms are implemented as sort functions on the read list. In our tool, we implement the following algorithms: deadline monotonic EDM, earliest deadline first EDF, least laxity first LLF, least slack time LST, and rate monotonic RM. So here's the trace files which are produced by our simulator for each simulation session. For each processed event, 4 fields are added to the file. First, the ID of the executing task, the deadline of that task, the time in which the task went to the running list, and the time in which the task left the running list. This file serves as an input for the front-end component, which we shall see next. So here's the Rbk Profiler Application, which can read trace files and command back-end application. You can drag application files to the window, configure a couple of parameters, and select the scheduling algorithm. In the future, we intend to improve this interface by adding information on the scheduling algorithms, scalability tests, and books and papers references for each of the algorithms. So here are some ideas for improving our work. First, we intend to extend our architecture to include other task models, which may include models for multiprocessor heterogeneous systems. We also want to include a multi-thread simulation environment, as we are aware that the current simulation model cannot efficiently simulate multiprocessors. There's a lot of work to do in the graphical user interface until it gets ready for any use in production environments, as well as we must implement more features to favor its use by students. We also consider to implement other features such as dynamic application admission, dynamic application parameters, and communication scaling. Thank you for attending to this presentation. You can find the repository of the project below, and you can also contact us through email. The addresses are shown below as well.
So let's go to the open for questions. If anyone has questions, be free to write on the chat or just open the mic. I have a question, Anderson. As I understood, the main target, or at least the main target that you wrote, is that you propose the architecture for academic scenarios, right? So then you talked that you are planning to develop the graphical user interface, but how are you planning to achieve this publicly, to go to the students, for example, with, so what are the next plans?
So hi everyone. So basically, our architecture it models a couple of the simulators we studied. So our target is to provide a small infrastructure for students to make their own simulators. So we believe they can learn from simulator during their undergraduate course. So this tool is basically directed for students. We see that we have a lot of industrial tools as well. We could not access all these tools. We are on the schedule to extract some features from these tools. We are in touch with 2 professors, so we intend to apply this tool in some disciplines, so people can manipulate the tool and give some feedback. So we expect a lot of change in the future.
Yeah, sure. Always when you have the user opinion, we open our mind about the new features and so on. So Professor Georgia Lima has a question here on the chat. He's asking you if you compare your simulator with others in the literature, for example, the SimSol. I don't know if you know this simulator, and if you compare with this one of the other one, or so. How do you see our approach in comparison with the others?
We have 2 kind of scenarios here. First one is comparing simulators, which we briefly discussed. It's a bit tricky because we have to extract the simulation model from both simulators, and so we can mathematically do the comparison. It's a bit different from extracting software features such as graphics and user inputs. So at one side we have mathematics. It's formal verification. Does the simulation work? How can we measure the time for the simulation to finish? This is one side of the coin. The other one is how is this simulator useful for people? How can students manipulate it? What are the features we implement in the simulator? So I think at this time we are not interested in comparing simulators, because some simulators, those one industrial tools mostly, we cannot extract their simulation model because we don't have we don't have access to their source code. Some of them I can remember the names now, but we can see through the documentation what the models are. But as far as I remember, we can't create a mathematical model for most of them. I can't really remember one we could. So we have to explore this kind of comparison later. There are no interesting features.
Okay. So I don't know. I consider this application with the student and the opinion of the students of your approach in comparison, or opinion of the academics, professors as well. Comparing your approach with the others in the literature, maybe it's more important than simulate. Of course, that your simulator should be accurate. Otherwise, it's seamless. But I don't know if I'm wrong, but this comparison could be done in the sense of getting the feedback from professors and the academics in general. So the Professor Márcio Kreutz is here also. So he has a question. He's asking if you plan to simulate over hardware models, for example, using System C. Do you plan to go in this direction as well?
This simulator engine, we have an engine inside our tool. It's been used before for simulating hardware. We actually have a hardware platform, an MPSOC, which we use the same engine to simulate. So we kind of reuse that engine into this work. But I'm not sure we can mix hardware and software simulation for real time. we have not touched that yet. Still, we are working on multiprocessor systems, so we expect it to simulate wood-threaded applications in the future. And our hardware model, it is capable now of simulating many core systems. Maybe in the future we can join both simulators, maybe make one calling on the other, or make a single software from both tools. But I'm not sure the directions for many core systems yet.
Okay, so we are on the time. So thank you again, Anderson. Congratulations for your work, and thank you the professors who made questions. And we hope to see you and see your work in next SBESC in other conference. So thank you again. So let's switch back to the third work. The paper is Verifying Security Vulnerabilities for Blockchain-Based Smart Contracts. The authors are Nedas, Mato Ledicius, and Lucas Cordeiro. So let's see the video.
Hello, my name is Nedas, and today I'm going to give you a presentation about the project of verifying security vulnerabilities for blockchain-based smart contracts. The supervisor of this project is Lucas Cordeiro, and the project was conducted at the University of Manchester in the United Kingdom. So today I'm going to give you a short introduction about the project, its aims and objectives, and main motivation and contributions of this project, as well as some short background theory about what this project is about, and also the most important part is the evaluation and analysis, as well with some conclusions given at the end of this presentation. So starting off, well, blockchain technology is relatively new, and it becomes more and more popular, and more people are interested in the field. With the new technology, there comes some new opportunities, for example, secure sensitive data transfer or electronic voting systems. The most popular are probably cryptocurrencies, Bitcoin and Ethereum, to name a few. And because blockchain technology is being relatively new, and as any new technology, it poses a cybersecurity challenge which has to be solved. The main objective of this project is to find out the best publicly available Solidity smart contract static analysis tool. And the more specific aims are to write the contracts as tests for the verifiers to check their accuracy and efficiency, and also performing benchmark tests and perform analysis and given benchmarks and the accuracy to see which static analysis tool is the best. Now, why on earth is cybersecurity important for the blockchain technology? Well, firstly, unsafe smart contract code is equal to financial losses, and the most popular cybersecurity incident, let's say, was the DAO attack, which happened in 2016, and $50 million worth of Ether, that's a cryptocurrency, was stolen and never returned back to the users, and applying inflation, that would be over $5 billion in 2021, which is quite a large amount of money lost. There are also other attacks such as parity wallet hacks and integer overflow, 51% attack, which is also quite interesting if you want to read further on that. Also, unsafe smart contract code is equal to system abuse and illegal exploits, and there are some examples, for example, King of the Ether Throne game or Governmental, where attackers managed to look at the smart contract code to find vulnerabilities and abuse them and render those games either useless or they can exploit them. The main contribution of this project is the creation of Solidity smart contract tests, which may or may not contain security vulnerabilities. That means some contracts are just like canary tests to check for false positives in the verifiers. Also, a very important contribution for the smart contract test is because the smart contract code is written with respect to the already existing cybersecurity properties. For example, the CIA triad, confidentiality, integrity, and availability triad is a very important point in cybersecurity, as well as the CIE CERT's coding standard, primarily written for C programming language, but because its concepts are very universal, let's say, we've managed to adapt them to the Solidity programming language and smart contracts as well. Now, going to the background a bit, so blockchain, probably most of you know already what it is, but just a reminder that it is a write-only list of data structures called blocks, chained together into a list called a chain, thus the name blockchain. It's not bound to any specific applications, although cryptocurrency is probably the most popular. And in order to submit a block onto the blockchain, it needs to be approved by a consensus mechanism. And the Ethereum blockchain, more specifically, it contains states, transactions, and blocks. Here you can see an example of a Bitcoin blockchain. It's not Ethereum, but it's the working principle is very similar. So you see each block is chained together, and each block contains a timestamp, previous block's hash, a nonce to ensure freshness, and some hash data in it. So smart contracts, formally speaking, these are a set of rules and protocols which are deployed on the blockchain in order to verify and validate the transactions between users. And it is a main interaction point for the users with the blockchain. Smart contract codes can contain malicious code, and they can be exploited. Luckily, we have static analysis tools which can verify the code before deploying the smart contract code onto the blockchain. Now, how the smart contracts can be verified? As I've mentioned previously, you can verify with static analysis tools and methods. For example, lexical data flow analysis, symbolic execution, and model checking are one of those most popular smart contract verification methods. And now I'm going to introduce the tools, the smart contract verifiers used in this project. So firstly, we start off with a Remix integrated development environment plugin, which was written in JavaScript, and it uses a detect and report approach. So not much maths is being used there, and it uses ASTs for detection and evaluation of vulnerabilities. It's fast and easy to use, so it's very, let's say, programmer friendly. Also, we have used Sliver, which is written in Python. It works similarly to other SMT-based bounded model checking tools, which is basically the source code is being converted into an AST, then to the control flow graph, to the intermediate representation, and then it's being analyzed, and then the results are being printed out. And Sliver has over 75 different vulnerability detectors in it. We've also used Oriente, which is also written in Python, and it uses an Z-free SMT solver. It catches only 4 types of vulnerabilities: call stack vulnerability, money concurrency, time dependency, and re-entrancy bugs. It's already outdated. Probably the last update was over 5 years ago, but it's referenced quite often in other articles and papers, and that's why we have decided to include into this project as well. Nephrol is another Z-free SMT solver static analysis tool, although it uses its custom backend called Laser Ethereum, and it works on very similar concepts as Sliver and Oriente. Its main advantages is that it has a vulnerability detection list, which is well documented and very useful for programmers. And SmartChuck, it's a Java written static analysis use, which uses Antler and the custom Solidity grammar to build its own abstract syntax tree, and then it generates an XML parse tree acting as an intermediate representation, and then it uses detect and report on that and report the vulnerabilities. And this is basically the life cycle of a Solidity smart contract, so how it works. So first we write a smart contract test, then we check if it satisfies the cybersecurity properties. Not all of them satisfy. And then we test out with the static analysis tools, write down the results, and then we do the resource management test with CPU loads and memory loads, and then we write down the results, and we repeat the cycle. We're talking about the tools. So we've used a medium, say, medium-end laptop, which used a Linux operating system with a Ubuntu distribution. And we've also used two benchmarking tools, an HTOP, which is basically an improved version of a top tool, which is already inbuilt into Linux, and Hyperfine, which allows to semi-automate the tests. So the performance metrics, there were three of them. So first one is accuracy. Obviously, the more accurate the tool is, the better. Speed. We don't want to wait ages for the static analysis tool to finish, and also CPU and memory consumption. So we want to have that tool to run on a normal computer, let's say with normal specs. Now I'm going to talk about the smart contract tests a bit and give you some practical examples which we had in this project as well. So the first example is this double spend vulnerability. So we have a smart contract allowing users to book a hotel room and pay a booking in Ether, which is, well, very convenient. And we have two functions. We have a function book and receive. So book allows to book a room in a hotel. It also checks if a user has enough money to pay for and the room is not occupied. The function receive does not check for the availability. That means the rooms can be overbooked. The problem is that function receive, it's an inbuilt Solidity function. That means when you call book, you call receive as well. So calling book and receive gives only one room for the price of two, which is not very nice. So here you can see that the function book and receive, we do the same operation, but we check for the availability in function book, but not in receive. That means when we call book, we book the room, we pay free Ether, but when we call receive, we also pay free Ether and we get the same room, which is not nice. The second example is about dead code. So dead code basically means a piece of code which does not contribute to the final answer or the desired answer. And here we have a smart contract which transfers Ether to owner from user after some calculations, and there are some functions primarily do something else which takes the user's Ether into account, but its returned result does not go any further. That means it takes a long time and consumes a lot of CPU and memory, and it's not very efficient. And here you can see that the variable answer here is not used anywhere, but the variable amount is. So the function do something else and do useless calculations are basically meaningless. And the static analysis tools, which are prone to code explosion, are very, very susceptible to this one. So for analysis, we've used all 5 static analysis tools as mentioned in this presentation. Each test was run 10 times with each static analysis tools. That means there were 130 times for each static analysis tool, and in the grand total of 650 test runs in total. Benchmarks were divided into 6 parts. So the first one was the normal conditions just to check for the timings. The other one was for the resource management. Then the third test was the CPU stress test. We used 100% of the CPU consumption. And then there was the 77% memory load and the 90% memory load. And the final one was the CPU load plus the memory load to see how it works under very difficult conditions. And the main goal here is to find out the fastest and the most accurate static analysis tool. And in this table, you can see on the left side, there are the test numbers. And on the top, there are the static analysis tools. And letter Y stands for the vulnerability found, and N stands for vulnerability not found. And we can see here that a sliver was the most accurate, while Oriente and SmartCheck were not so. And in this graph, we can see that the average running times, for example, for Sliver and Remix, we were kind of consistent, while Oriente and Nephrol were jumping across the tests. Here for the CPU and memory consumption, you can see as well that some static analysis tools were very resource hungry. For example, Nephrol, and CPU consumption was almost always 100%. With the memory consumption, it's also, you can see that Oriented jumped a bit through the tests as well. So the results, you can see that the sliver was by far the most accurate and balanced on resource management out of 5 analyzers tested. The Remix IDE plugin was also quite good. The Nephrol is quite resource hungry, so it can be prone to timeouts, but it also detected a significant amount of vulnerabilities. SmartCheck is comparable to Nephrol in accuracy. Its resource management is better though, although that's quite interesting because it's written in Java, not in Python like others. And Oyenta, well, yeah, so age takes its toll, so by far is the least accurate static analysis tool, and it's quite prone to code explosion. So for conclusions, the main contributions of this paper is the compilation evaluation of Solidity smart contract tests, which are written with respect to the cybersecurity properties. As much as we know that not many surveys or analyses were carried out, where smart contracts with security vulnerabilities had risk assessments or comparisons to the CIA triad, and we think that's quite an achievement unique to this paper. The obtained data allows prioritization of vulnerability checking, so in industrial environments, there's also always this trade-off between accuracy and speed. So some people have to choose whether they want to have it done quickly or they want to do it in a very accurate way. And for the future work, so there's going to be the SBMC static analysis tool extended to perform in-depth security analysis for Solidity smart contracts from the cybersecurity perspective, because SBMC currently is only adapted to C and C++. So, thanks for listening.
So, as none of the authors is present, let's go to the paper number 5. It's named a multi-site characterization study on failure causes in system and application software. The authors are Caio Augusto Rodrigues dos Santos, Rivalino Martins Jr., and Christoph Trivedi. So, welcome, and let's see the video.
Hello, my name is Caio, and today I am going to present the paper A Multi-Site Characterization Study on Failure Causes in System and Applications Software. It is undeniable that computer systems have become the backbone in the modern society. In this scenario, their failures may lead to simple inconvenience to risking human lives. Moreover, reliability is a major concern not only for critical systems, but also for commercial off-the-shelf software. For example, the US Navy navigation systems run on top of regular Windows operating systems, so the OS layer should guarantee at least the same level of reliability expected for the user applications. A fundamental need for software reliability engineering is to comprehend how software systems fail. And the first step toward this understanding is to characterize the software failure causes. Regarding previous works, we haven't found studies that characterize software failure causes at the level of technical details we consider necessary for a better understanding of their nature. Moreover, most related work is not based on a robust dataset in terms of size and diversity. Therefore, in this research, we perform a comprehensive analysis of the cause of real software failures that were collected from hundreds of computers located in different workplaces, and we consider different properties of each failure cause analyzed, including their type, context, software layer, and code where it manifested. Our main goal is to answer the following research questions. What failure causes are more prevalent in our dataset? What are the types and themes of the most prevalent failure causes, and where do they manifest most? We used a commercial off-the-shelf operating system software, the Microsoft Windows 7, and the user applications running on top of it as our object of study, because this is still one of the most used desktop operating systems. Moreover, Windows 7 provides detailed failure registries through its reliability analysis component, also known as Rbk. The rack collects some data about the failures and stores it in these fields like the computer name and the time when the failure occurred. These 6 highlighted fields are the main fields we used in this research, and they were used to uniquely identify each failure event. Our work sample comprised more than 40,000 failures obtained from more than 600 computers running Microsoft Windows 7, and the data were organized into 4 groups. G1 comprehends failures in computers of undergraduate teaching laboratories. G2 are from the university's administrative departments. G3 contains failures in computers of a corporate environment, and G4 is a heterogeneous group and contains failures in computers from different environments such as household, corporate, and academic, among others. In our dataset, user application failures are predominant compared to OS failures. Note that more than 80% of the failures occurred in user applications. Specifically for OS failures, some previous works considered as OS failures only the failures that occurred in the kernel space. But we know from the OS theory and practice that modern operating systems have several of their parts executing in both kernel and user spaces. Therefore, we adopted an approach introduced in this 2013 paper from our research group to categorize OS failures that occurred in both kernel and user spaces. So based on the fields event identifier, product name, and source name of the rack record, we classified each OS failure into one of these 3 categories: OS application, OS service, or OS kernel. And note that the most common OS failures belongs to the OS service category. Since OS service contains the highest percentage in failure events, we analyzed the field source name in the failure records from this category, and we found that 17 types of OS service failures were related to software updates performed by the Windows Update Service, which is the standard software update mechanism in Windows 7, and these 17 types corresponded to 88% of the total number of failures in the OS service category. Given the prevalence of OS failures related to software updates, they were clustered into 17 subtypes within the type Windows Update Service. An analysis of these 17 subtypes showed that only 4 subtypes represented most of these failures. We also collected different numerical codes in the fields message and insertion strings of the failure records, and we were able to identify the failure causes by searching for these codes in Microsoft's documentation. And this is an overview of the failures stratification. Note that we used exception codes to identify the causes of OS service, OS application, and user application failures. For OS service failures related to the Windows Update Service, we used error codes. And to identify the causes of OS kernel failures, we used stop codes. In addition, note that in the other categories, the fail code is always a part of a running process executing in user space. Differently, the code where OS kernel failures manifest is not a process, but a routine executing in kernel space. After analyzing the meaning of the numerical codes, we mapped each code to a user-friendly name, which is the failure cause type. And we also defined the theme, which means the context of the failure cause. In this example, the first code is mapped to the type access violation, which is in the context of memory addressing. Note that the second code also occurs in the context of memory addressing, but in this case it is mapped to the type heap corruption. And now I am going to present our main results. In total, we found 11 themes of failure causes in our dataset. The main themes per category are hardware-software interaction for OS kernel failures, install update for OS service, and memory addressing for both OS and user applications. In fact, both OS and user applications show similar patterns in their most frequent failure causes. This happens because technically OS application and user applications should not present significant differences. And the category OS service is the only one where we observed failure causes from all teams. This may have happened because OS service has a long runtime length, running in background and performing a high number of interactions with other processes and resources. These are the most prevalent failure causes observed, and they were ordered by their frequency in the dataset. Note that the first two entries caused more than 70% of the failures. And these are the types and themes of the most prevalent failure causes. The types access violation and heap corruption correspond to 49% of all failure causes in the dataset, and both types are related to the same theme, memory addressing. And a frequent trigger for access violation is a null pointer dereference. Heap corruption occurs when the code damages its dynamic memory allocator's data structures, which can be done by situations like stack overflow or overrun in buffers. Next are failure caused by hangs. Note that this is the only failure cause in our dataset that doesn't have a hexadecimal code. And there are many reasons for an application to hang. For example, waiting for events that never occurred due to software or hardware issues, deadlocks, and others. And finally, we have the types unhandle exception and exit unhandle exception, which correspond to 7% of the failure causes. Unhandle exception in either managed or unmanaged code are ultimately dealt with by the Windows kernel that forcibly terminates their process. And the main difference between unhandle exception and exit unhandle exception is the moment when the exception is raised, in which always occurs during the process termination in the exit unhandle exception, and for the unhandle exception it occurs before that. And these are the top 10 fail codes in our dataset. In this case, they were ranked based on the number of groups, computers, and frequency of failures. Note that the most common are user application failures. We also observed a high number of OS kernel failures related to the interaction between the display device driver and the video card. The only representative of the OS application category is the Explorer.exe. And finally, we also observed some software update failures from the OS service category. And now I am going to show the fail codes in detail for each category. The Internet Explorer browser is the program most affected by the failure causes analyzed in the user application category, followed by Microsoft Word and Microsoft Excel. These are well-known and widely used programs which may expose them more in activating different failure causes. In case of OS kernel failures, the video TDR error is the most common failure. This occurs when the video card is so busy serving the application's requests that may indicate a system hang. When this happens, the Windows kernel tries to detect the cause and recover from the possible hang, which is called Timeout Detection and Recovery, for short TDR. And the video TDR error occurs when the recovery procedure is performed and fails after 2 seconds of trying to restart the display device driver. Some common root causes for this problem are overclocked components, defective parts, and others. The second most common is the driver power state failure. This failure occurs when a device driver requests the device to power up or down. Some common root causes for this problem are defective devices and outdated drivers. And the third place is critical object termination, which indicates that a process or a thread crucial to the system operation has suddenly exited or been terminated, and this may occur by different reasons. The most affected program of OS applications was the Explorer.exe, which is a file manager that also provides graphical interface components. And a failure in this program can prevent users from accessing files and running programs. The second is the MS Core SVW, which is a .NET Framework optimization service, and it's used to optimize the launch of .NET applications. The third place is RunDLL32, which is a program that allows the execution of a code from a library. Finally, for OS service, we observed that most failures are related to software updates, and the update installation of Windows OS core components was the program that failed most, followed by updates of the Internet Explorer browser and updates of the Microsoft Office. In conclusion, we observed that the most prevalent failure causes in our dataset are related to memory addressing, which can be explained by the ubiquity of memory operations in computer programs. And according to the taxonomy we adopted, most of these failures are introduced in programming time. Other relevant failure cause found was unresponsive UI. This type of failure cause is mostly originated at programming time, but external factors must also be considered, such as interactions with other processes. And analyzing all types of failure causes from our dataset, we note that most of them result in system and application crash or hang, which indicate the use of replication and redundancy as appropriate fault tolerance mechanisms. Diversity is another important mechanism, especially to mitigate the effects of failure causes like installation errors and video TDR errors. Note that like any empirical study, this research has limitations that must be considered when evaluating its results. The empirical findings presented are based only on our dataset, but we consider our dataset diverse enough to avoid critical biases. Thank you very much.
So thank you, Caio, for your presentation. So we have time for questions. Caio is here with us. So meanwhile, while you can think about the questions, and I can also start. Caio, congratulations for your work. Everybody knows about the failures that the operating system has, and also the drivers and also applications. But when we see that, it is a little bit scary. We know that we are running many important applications above this. So the question is, in your last slide, you talk about diversity as a solution. For example, the video card problem failure. What is it this really means?
Yes, diversity, specifically for the video card, we are meaning the configuration diversity, because most of the video card problems are caused by, for example, overclocking. So if you change the configuration in different devices, you may experience this failure just in one system and the other one, that because in diversity you create multiple configurations in different systems. So just that one that has the overclock will fail, and the service will be available.
Okay, thank you. So Anderson Dominguez also wrote a question here on the chat, and he asked if you have any direction on how to mitigate these errors. It's also a doubt that I also have, and also if the logs point to specific modules.
Yes, actually, Professor Rivalino just answered him based on.
Okay, sorry.
On the...
Yeah. Okay, we connected. Okay, so So then he wrote that based on the information you collected from the logs, it's possible to identify the faulty modules in many of the software components. Okay, thank you, Rivalino. And do you have some directions on how to mitigate these errors?
Yes.
I know they are very there are many. Should there be many recommendations because we have different types of sources?
Yes. In our work, memory addressing was the main cause of failures. And actually, Microsoft is aware of this problem, and they are trying to mitigate it by using a different programming language, like Rust. But this may have add other problems, and even the memory addressing still persists. So it is difficult to find a solution right away. But based on these findings, the programming or testing may focus on these problems. Like, we are aware of these problems, so we can direct the resources of trying to mitigate these problems.
Okay, so Professor Rivalino is also writing here. He wrote, direction should be planned for each target software. For instance, RPC servers faults may benefit from environment diversity approaches, like software rejuvenation. So it's another. Yes, it's very. You pointed one problem source. There's the programming errors, human errors, and Rivalino is mentioning the diversity, environment diversity here. So it's really very nice work with many implications. So yes, Kai.
Yes, in this case that Rivalino mentioned, the RPC server failures, they occur due to exhaustion of ports, where there is a RPC call, but the client never never closed the connection. So these ports are being used, are connected but not being used, and there is an exhaustion of ports, and the rejuvenation of the server side will actually clear all these ports to be used again. That's the diversity.
Okay, I see. Rivalino wrote again. Once we can pinpoint the most frequent causes, then it can help us to identify the effective approaches to be applied for different software. Yeah, it's a very, as I told, it's a very critical situation. We have many different sources, things from software, from hardware, drivers, and your work open many different windows for studies, and also maybe recommendations of good practice to programmers, to hardware and driver developers. So congratulations for your work. We are on time, so then we are jumping to the next work. So thank you again.
Thank you.
So the next work is work in progress. The paper is Assistive Technology for Fault Detection Development of Integrated Wearable Sensors to Smart Home System. The authors are Yuri Valadão, Ivan Müller, Thiago Rodrigo Cruz, and Guilherme Torres. So let's see.
Hi, my name is Thiago. I'm going to present this work called Assistive Technology for Fault Detection, the development of integrated wearable sensor to smart home system. The early detection of an emergency increases the chance to have an appropriate treatment. A possible solution is the use of assistive technologies, which in this work are used for fall detection of elderly people. Currently, 40% of the elderly live independently worldwide. Therefore, the use of assistive technologies is considered an important topic in the area of assistance for this large part of the population. Some important characteristics of fall detection systems are data acquisition of fall events, which can be obtained from wearable devices. The algorithm must be computationally efficient and low power consumption in order to be incorporated in wireless sensors. And it's important to integrate the fall detection system with a smart environment. So in this context, this work presents the development of a wearable device to detect falls. And this device is connected to a smart home system to trigger alarms when fall events are detected. The data communication uses an Enotion STM300 as a RF transceiver module. Inertial sensors are used to detect fall events, in this case an MPU 9250. A Raspberry Pi is used to receive the data from the wearable sensor, as can be seen in the figure. This board runs the Home Assistant application to send data to the KNX system. The KNX is an open standard for home automation. And figure 2 shows the developed prototype with the inertial sensors and the RF transceiver. In order to provide data to use as reference in the fall detection algorithm, an experiment was performed. The experiment considers 8 types of movement, 4 fall movements presented in figure 3, and 4 non-fall movements. These movements are standing, walking, sitting, and running. The movements are repeated 100 times by 2 people, a man and a woman. The variables considered in the experiment are the acceleration, angular velocity, and inclination on the x and z axis. The fall detection algorithm uses 3 methods to estimate the angular value. The first is a simplified estimation that considers the raw data. The second using the arctangent, and the last approach obtains the angle from merging accelerometer and gyroscope sensor data through a complementary filter as shown in figure 4. The results of this preliminary experiment are presented in these graphs. Figure 5 represents the x-axis angular values and figure 6 the z-axis. The graph is divided in 4 sections, representing the 4 movements considered, and each line of the graph represents a different method to estimate the angular values. As can be seen, in the first 2 options, the noise is bigger than the third method because they only consider the accelerometer data. This is data from the forward falling movement. So compare data from non-fall movements with data from fall movements, we can identify the limits to use in the fall detection algorithm. This is a representation of the proposed algorithm. From data obtained in the first experiment, it was possible to set the acceleration and angular velocity limits. So when the system identified that the collected data exceed these limits, the algorithm passes to a second phase, where the estimated values of inclination are analyzed for 5 seconds. This phase is important to differentiate the fall event from a normal event, for example, just lying in the bed. And after this analysis, if the event is identified as a fall, the alarms are triggered. Here represent the results, where case 1 and 2 refers to 2 different people. a man and a woman. And as can be seen, none of the non-fall movements were defined as fall events, but some of the falls were not identified as fall events. Here we present a comparison with previous works. The selected metrics are the sensitivity and specificity. Sensitivity evaluates the performance based on false negatives, where the user fall but the system does not identify it as a fall. And specificity is based in false positives, where the user do not fall but the system identify it as a fall event. The proposed algorithm reached average values of 96 and 100% respectively. As the result presented, the prototype performance is satisfactory, but estimation errors are generated. These errors can be associated with different body characteristics. Therefore, a possibility for future work is to add an algorithm calibration method based on different body characteristics in order to improve the performance of the system. Also, the miniaturization of the prototype is also important to make it less invasive as possible. And these are some references used in the presentation.
So, thank you. I guess Thiago is here, right?
Oh, yes, I'm here.
Okay. So, thank you, Thiago, for your work and congratulations. I have some questions for you. The first one is considering the device, the hardware. The idea is the wearable device only collect the data from NPU and send to the Raspberry Pi, which will make the computation, or the computation will be done in the wearable computer, in the wearable device.
Yeah, so we have some pre-processing data in the wearable device, but the algorithm of fall detection is running in the Raspberry Pi.
Okay, so then you have to consider the trade-off, right? Because the trade-off between the data rate that you send to the Raspberry Pi should be enough to get all the time series, right? All the data to avoid the error.
Yes, to be able to identify the false.
Yeah. So then you use Wi-Fi, right, to send data.
Sorry?
Do you use Wi-Fi to send data from the wearable to the Raspberry Pi?
Yes, it is a wireless communication.
Okay. Using UDP or TCP?
Well, this is specific information I don't have right now.
Yeah, okay. I'm asking because I'm working with similar scenarios that this is a problem that always we have here. So the other question would be more in the direction of your data. Did you try to find some data set of this NPU to detect this kind of situations?
Do you mean data set from fall events?
Yes. Because
no, actually, we created our own data before doing the algorithm.
Yes, I see. Because also there are some works, as you pointed in your reference. There are other works that is investigating this case, and then maybe some of them published their data set, because it's always complicated to compare your work with the others, because each one uses its same or they own data set. So then compare one data set with the other data set is always hard. So maybe a good point of comparison would be if you get your algorithm and validate with the data set of the other paper. Then you can really compare the results of your work with the others. But it's just a suggestion. I think it's very nice work and very relevant to the scenario. We are on the time of our session. We have some time for some more questions. Then also another point. I don't know if you, of course, that you have. You are working on the wearable device. There are also these very popular smartwatches that can also collect this and can detect some events. And did you plan to maybe to evaluate them, or maybe to compare the accuracy of this software, these apps from these smartwatches?
Well, I believe it's a good. There's a possibility to compare with devices that already exist, but we didn't consider in this work.
Okay. So thank you again, Thiago. And
okay, thank you.
Welcome. So we are closing our session. This was your last but not least work. So thank you everybody for all the. First of all, thank you all the authors that presented your works here. Thank you for all the audience that was here following our session, and also thank you for those who made questions and contributions. All the authors are available for future questions, and then you can see in the proceedings the contact of everyone. So hope to see you soon again. So be safe, be healthy, and thank you.